Well, thanks, Jack. Yes, the title of this talk is Towards a Silent Aircraft. I can be quick with this view graph because we've seen it already. But one of the messages that we would take from this plot of noise against time is that some of the trade-offs due to going to large bypass engines have now been cashed in, and it's getting increasingly difficult to reduce noise through incremental means. And yet, aircraft noise still constrains the expansion of air traffic. No one wants an airport in their neighborhood, or even extra operational hours, or even a new runway. So the predicted expansion of aerospace, and it's significantly predicted to expand over the next 20-odd years, could be very much constrained by community objections, particularly to noise. Now, if there's one thing I've learned from Shon Ffowcs, it's to try and ask the question in a different way. So suppose instead of saying, this is what aircraft look like, how can we model it, how can we make it quieter, we turn the question around and say, if noise is really a constraint, what should an aircraft look like? And that's what we're doing in the project that Tom and I are going to talk about today. So we're asking if we have as a target a radical reduction of noise, and by radical here, we're thinking of an aircraft that should be imperceptible outside the airfield boundary in an urban environment. So not imperceptible in the heart of the country or over rural Wales, but in an urban environment, it should not be a nuisance to the community.
Are you threatening to have an airport near me?
Just a wind farm, I think. And in discussing this, Tom and I will be drawing on preliminary results from the Silent Aircraft Initiative, which has been running just about a year, and it's a collaborative project between MIT, Cambridge University, and a growing community of partners. And it's funded by CMI, which is the Cambridge MIT Institute. Again, we've seen this one already. The message here is at takeoff, fan noise and jet noise is really important. On approach, the fan is off design, becomes even more important, and we've got a large contribution from airframe noise. So what can we do about those? Well, first of all, design with low noise operations in mind is absolutely crucial, considering how the aircraft will be operated in order to minimize noise, feeding in to the design very fundamentally. To achieve any of this, we're going to need much greater integration of airframe and engine. And for example, using the airframe to shield the engine noise from listeners on the ground, and also to provide room for extensive acoustic liners. Current ways of developing high lift will just not do. Slats are too noisy. And drag. If you think about it, an aircraft at altitude is going fast, it's got to descend and come into land. It's got an awful lot of kinetic and potential energy to dump in doing that. Currently, that energy is dumped into the air, unsteady motion in the air, in really noisy ways. The pilots lower the undercarriage much earlier than they need to for operational means. That's to get the drag up so that they can dissipate some of their potential kinetic energy. Flaps are used, again, almost like air brakes to slow the aircraft down, but these are noisy ways. That energy is going into unsteady air motions in a way that's noisy. So we want to address those. We need ways of getting drag in particular without increasing noise. Jet noise, we've got to do something about jet noise because it's such a large component of aircraft noise. Yes, we can do things with jet noise that will reduce it by a few dB, but if our target is a really radical reduction, then the most successful way of reducing jet noise is simply to reduce jet velocity. In carrying out this work, we have an extensive community of partners, which I've listed there. They range from manufacturers, Boeing and Rolls-Royce in particular, Operations are important, so we're working also with airport and airline operators, air traffic control, regulators, CAA, and even a community action group. And with some other universities, and I'm very pleased that Cranfield, with their extensive experience of aircraft design, has very recently joined this project. We're carrying out the work using industry design tools, and on the airframe side, we're using Boeing's WingMod preliminary design tool, which checks something like 150 constraints around the flight envelope. So this is making sure some of the key structural aspects, some of the key control requirements are met. On the engine side, we have installed in Cambridge Rolls-Royce's performance code, Genesis, and an in-house noise prediction, VNO2. And we're using this where we can, and our own models and other models from the literature, where we move way away from current practice. And throughout this project, there's really been substantial technical interchange between academia and industry. This isn't obviously something that universities can do on their own. On the other hand, industry doesn't often have the motivation to take such a very long-term view as we're able to do in this project. And that means that there's a whole range of acknowledgements to people who've contributed ideas and calculations to this work. So the framework of the project, I started by saying how important the way in which an aircraft is operated will be to meeting these noise constraints. So we have an ops group, but also an economics group looking at the impact on airline, in particular, economics from operating a silent aircraft, increased operating hours, quicker turnaround, and so on. Right at the heart of the technical design is the aircraft integration, and that integration has a substantial acoustics aspect to it, so we try and maximize these benefits from shielding. We've got a team looking at technologies for quiet airframes and novel engine architectures for low noise. We have to set the size of our aircraft, and we asked our industry partners what they would recommend as a mission for this conceptual design. And the advice from them was to go for the smallest aircraft that could be scaled up. And since we're looking for some shielding effects, it can't really be too small. So based on that, plus a credible market from the airline economics people, and also looking for something that's technically feasible, we've set ourselves with an absolute target of imperceptible. That gets harder, obviously, the bigger the aircraft. So we've actually gone for a 250 passenger aircraft, a range of 4,000 nautical miles, and setting the cruise Mach number to be 0.8. It will have a silent mode of operating, of takeoffs and landings, but only under normal conditions. In other words, if it's hot and high, or if there are extreme crosswinds, or any emergencies, the aircraft could land in a different mode, which would be noisier. So silence only under normal operating conditions. And of course, it has to do this while still meeting the requirements of being competitive in terms of fuel efficiency and reliability and so on. So these ideas on operations and shielding and more extensive liners will get us over some of the noise sources. But with jet noise, the reliable way of getting that done will be to reduce the jet velocity, simply because the sound goes with a high power of jet velocity and linearly on area, whereas our requirement for thrust will go scale on velocity squared times area. So we're going to turn the usual question around and say, if we have this noise target of imperceptible outside the airfield perimeter, how big should the nozzles be? How big should the jet nozzle be? And here we're using a standard prediction, which also checks out with A0. If we take our noise target and initially start with a very simple takeoff profile, then we come up with a jet area of 16 square meters. When we begin to optimize on operations by having a cutback and then optimizing the flight path while still meeting the legal constraints imposed by FAA, CAA, we can reduce that jet area to just over 10 square meters. If we compare where we are with current and the next generation of engines, our target aim is to be some 25 dB quieter than that. And turning this around, if we have 4 engines, it says we need to have an exit area which is about 3 times larger. So large exit area of engines here. The difference between the different number of engines is based on regulators' requirements as to how soon the cutback can be made given on the number of engines that you've got. So if we go for 4 engines, we need an exit area 3 times current technology. So what would those engines look like, and how can they behave well in cruise, and how can they actually be fitted onto an aircraft? And at this stage, I'm going to toss that as a challenge across to Tom, who will pick up from there.
Thank you. So as Anne says, these engines are approximately 3 times the size of the aircraft, of current engines. So if we go this route, then in theory we've solved the jet noise problem. And we have these other issues to deal with. In order to get a very large engine inside an aircraft, and in order to go for an aircraft shape which will give us the required amount of shielding that we're looking for, we've been working with Boeing on some of their futuristic designs for potentially blended wing body. You may have seen studies that have been done recently along these lines by Boeing. These blended wing body aircraft are passengers sit in the central compartment here. It's an all-lifting surface. It's something like a flying wing. And if you look at it in cross-section, you'll see that the passengers sit here. There's a standard cargo bay underneath, and there is this region at the back here, which is, you have to have an emergency exit there, but there is actually quite a region for power plant installation there. This original design for Boeing, they had their engines up above the top of the wing, but I'll talk about some of the things that you might wish to do. So these are big engines. We're talking about 2.5 to 3 times the size of conventional technology. If you look at where you could stick these engines on the airframe, you saw the Boeing designs actually had some engines up above the wings, but you might also consider actually burying these engines. And this is, as we'll see later, is the route that we would wish to go. We are going to think about putting engines in this region here. And if you look at this blended wing body shape, there's actually quite a lot of vacant space here. One of the advantages of this blended wing shape is that there is actually quite a large volume within the airframe that's available. And so our sums that we did said that we could fit between 2 and 15 engines within this 15-meter frame. This 250 size seater aircraft, it's about the size of a 767-200, and its duty is rather similar. If you look at how long the liners you need to take to absorb the turbo machinery noise, then you actually need a significant length If you look at current liner technology, you need somewhere in the region of 6 engine diameters in which to actually absorb the noise to actually get you down to silence. We see later when Anne comes back that you can get quite a lot from shielding, so your forward requirements are not that great, but you do need a large section behind the engine if you are to have a chance of absorbing the turbo machinery and the jet core mixing noise. So question, how would you stick the engines on this airframe? The first option is to go for podded, and if you had a podded engine with the liners big enough to actually do all of the turbo machinery noise absorption that you need to do, it would look approximately like this. This is a sketch for how big these engines would be for about a 4-engine installation. Putting the airframe, the engines up here is actually not a good thing to do from this type of aircraft design. They have a tendency to give you a pitch down moment. It's quite a problem actually keeping the nose up, and actually putting the engines up here is a poor move. The large wetted area of this type of installation is really going to hit you, and the pylon weight and increased structural weight to hold the engines there is a serious issue. But sticking the engines up there does put them in the clean flow, and in theory, if you haven't embedded them, you can actually get at them easily for maintenance. Other options that you have are actually to start bringing the engine down. And you might think about having this engine as being partially embedded. You've lowered the thrust line, so Boeing are quite happy that it enables them to maneuver this aircraft a little bit better. There are weight savings because you don't have the pylon and all the support structure of the back end in order to support the aircraft to survive a crash. And there is a drag benefit because you've now started to bury some of this area here, and you're actually still capturing clean flow. We would like to go further than that, though. We would like to think about engines which are actually fully embedded. And this again is a lower thrust line. So again, there's a trade-off there. And now there's a further drag benefit. The further drag benefit means that you've now effectively got the bottom half of this nacelle actually counting as part of the airframe. So there is no drag on this part. So there will be a significant drag benefit by dropping the engines further. And of course, we've got the lower thrust line. The disadvantages are that you have to cope with an inlet boundary layer now, which is being ingested over the airframe. And that, added to the curvature in the duct, can give you big inlet distortion problems, and potentially non-uniform flow reaching the engine. But if you think in terms of fuel burn, there is an advantage in doing this. That if instead of actually taking clean flow and accelerating it to a high jet velocity, you actually take flow which has been slowed down by the airframe and re-accelerate that, then you're accelerating that for a given momentum increase to a much lower speed than if you had taken clean flow and shoved it out as a higher jet. So there's a propulsive efficiency benefit to doing this. Okay. So there are other reasons why you would wish to do this if you can get away with it. Fuel burn advantage. Okay. So we have these problems with these large engines, and the big problems are to do with the size of them. The area is approximately 3 times existing, and that comes down to about 2.5 times the engines that people have got planned for the 787. And that corresponds to a fan diameter of about 1.7 times existing, 1.6 times planned. And we have the usual problems that the aero engine manufacturer has to juggle. You want good cruise performance, so I'll talk about propulsive efficiency. The engine will be sized for top of climb. This is the maximum non-dimensional thrust requirement, and this is where the engine is operating its highest non-dimensional speed. And you always wish to keep the weight as low as possible. So large fans are at an immediate hit on weight. And the fan size is effectively the overall driver as far as weight is concerned. Now, you can look at how weight varies with fan diameter, and it goes like some power of fan diameter. Not quite 3, but about 2.5. Okay. And but there are some advantages to going to a larger number of smaller engines. And the studies that we did said that If you went for a large number of small embedded engines, then you would save about 22% of the total engine weight if you'd gone for 2 podded. Okay. Now, in terms of actually choosing the fan diameter, you have to ask the question, if this is 1.6 times what people have got planned in the future, why did those decisions come about, and what are we doing that's different, and how are we going to get around this? As I said, this initial design of aircraft is a 767 size of aircraft, and if you look at where the 767-200 engines are, they're around about here in terms as our baseline engine. If you look at where we would be on future technology, that you would like to operate here, two podded engines will take you to about a 25% increase on the 767 engines. But this has already been cashed in, and this is where the 787 engines are going to be operating, somewhere in this region. If your engines are podded, the more engines you have, then the bigger wetted area you have, and the bigger the hit on nacelle drag is. And so the driving force is to go to a smaller number of engines. If you can in some way bury the engines, the trade-off is that you're losing the drag on quite a lot of the nacelle, and there's actually an advantage to going to a higher number of engines. So if you think that you're going to go embedded and you go for a larger number of engines, shall we say 4 or 8, then your bypass ratio or your engine diameter is actually 25% bigger than what is planned in the future. So of that 1.6 hit necessary to make these engines silent, the decision to embed them means that that hit is now only about 40%. Okay. The engine is still sized for top of climb, and it still has to meet these various requirements. And once you've chosen an engine fan diameter, then the fan pressure ratio comes out of the wash. And but we have to get these engines off the ground with maximum jet area, minimum jet velocity. So the design requirement for us is good fuel consumption at altitude, but maximum engine flow capacity at takeoff, but the engine sized for top of climb, not too compromised. And as I say, at the moment, you would be thinking of a compromise of about 40% increase in fan diameter. Now, when you go to these high bypass ratio engines, you have significant problems, and I'll just run through some schematics to show you how the engine manufacturers happen to get around these at the moment. As you increase the fan has to live somewhere on the fan pressure ratio, fan capacity map, and as you increase the speed, the engine performance moves up according to the arrow that I've drawn there. You're limited to stay in the stable region. You're limited by fan surge considerations and flutter, etc., which also hit you somewhere up in that region there. The highest efficiency tends to be in this sort of region, and you would like the top of climb and the cruise, the altitude working line, to be as close as possible to this peak efficiency region. As I say, top of climb is the highest design, point on the engine thrust cycle. Cruise is somewhere around here, around about peak efficiency. But the problem with low bypass ratio engines is when you come down to takeoff, if you've got a fixed area nozzle, the takeoff working line tends to be right up and probably the wrong side of the surge line. So what people are doing at the moment is compromising that efficiency by dropping the top of climb cruise and in order to get the takeoff working line somewhere in this region. And on this scale, what it is that we want to do now, we want to add our pressure ratio for quiet takeoff. And low jet velocity, low pressure ratio at takeoff, we would like to be somewhere down here. And you cannot do this. Okay, but you can do this if you decouple the altitude performance from the takeoff requirements. And so you can do this if you go for some sort of variable cycle engine. And the simplest variable cycle engine is to think about a nozzle opening and closing. With the nozzle closed, you can take the optimum design point, peak efficiency, and best optimum fan size at top of climb. And then if you open the nozzle for takeoff, you can actually, so you're operating this engine as if it was a ducted propeller, and the installation is just simply to absorb the noise. And by opening the nozzle right up, you can actually operate right down here. So this saves you about another 20% in fan size. So in terms of optimum fan size, we're now just talking about an engine which is about 10% fan diameter bigger than you would have chosen if you had gone the traditional route. Okay? Our exercise has been taken through using the Rolls design tools, and we've actually designed a fan to do this. You'll see that our bypass ratios are up around about 15.5 to 1 at top of climb. Fan pressure ratio top of climb 1.45. If you think about future generations of standard turbofan engines, they're on about 10 or 11. We've designed this. High bypass ratio turbofans have a problem with small blades, and so we've put in some radial turbo machinery there to actually try and get around that. Towards the back of the annulus here, we've actually got some radial turbo machinery. And you cannot get this sort of bypass ratio without some sort of gearing. And this design for our engine is a 3-to-1 geared fan. This fan is, as we've said here, about 85 inches in diameter. And the gearbox is around about 3-to-1. And this is not desperately different to the requirements of, say, something like the Pratt & Whitney 6000 gearbox requirements. So these are all well within the current extrapolatable technology. Okay? And the SFC is actually competitive. Okay? In terms of number of engines, the studies that we've been doing, we'd actually like to go to a large number of engines, but the difficulties that we're having is actually getting the flow into them. There is a serious issue about getting these intakes to perform properly, and our first cut at this has been that we're going for 4 engine designs with individual intakes, and it's simply just driven by the difficulty of the aerodynamics of this pre-compression region without giving you too much drag on the back half of the airframe. We would really have liked to have gone for many engines which were actually buried with common nozzles, etc., common intakes, but that's difficult.